Alright, let's run it. The last new topic for Class 2, Unit 3-4, sampling and estimation. We'll go through essentially the entire chapter's worth of stuff. There will not be much that's necessarily new, just sort of recontextualized. What you'll find is that you pretty much use the exact same methods you've already been using for discrete probability and binomial probability for this area of study, and then just sort of applying it and ever so slightly changing things around to accommodate the specifics of the Chapter 17 stuff. And then yeah, that's pretty much it. From that point onwards, we'll be focused on SAC revision until everyone's done their SACs, and then exam revision. Exciting. Okay, sampling and estimation. What's going on here? Fundamentally, the only thing I want you guys to really understand about this area of study is how you compare it to discrete. If we recall how we handled discrete probabilities, it was essentially a matter of saying, like let's say we got our heads or tails thing, or our 3 boys, 5 girls, for instance. You would want to find out the probability of either selecting a boy or a girl, and you'd have a certain number of trials. Like let's say we're trying to select 3 individual students. Whether it's with replacement or without replacement changes how you handle that actual calculation. But basically, if you're selecting 3, you would have like your x equals 0, x equals 1, x equals 2, x equals 3. You'd have those integer values to say how many boys or how many girls you selected out of the total of 3 possible selections that you had. It was all integers. All sampling and estimation is doing is converting that to an equivalent fraction, an equivalent proportion. So rather than saying x equals 0, 1, 2, 3, you now have 0 out of, hang on, what would it be out of? It would be out of the total. So 0 out of 3, 1 out of 3, 2 out of 3, 3 out of 3. That's really all that's changing here. So when you then go ahead and look at some of these questions that we'll go through, right, like you'd have probability of x equals 1 is equivalent to saying a probability of p hat being a third, because you had 3 selections, 1 out of 3, rather than just saying x equals 1. So all I wanted to highlight there was that nothing has actually changed. It's just representing the x equals 0, 1, 2, 3 as their equivalent fractions. But okay. So, some new definitions. You've got the population proportion and you've got the sample proportion, both p and p hat respectively. What are these? Well, the population proportion is the number of elements in the population that has the desired attribute divided by the total number in the population. This is just your x over n that we know like way back when for fundamentals of probability. It's just how many things have what you want divided by a total number of things. Both of these equations are effectively the same thing. The only thing that's changing is whether you are looking globally across an entire population or locally within a given sample of that population. Which one you're using will depend on whether you're looking at p or p hat here. So if we look at a few examples, we got a math class, 3 boys, 5 girls. What is the proportion of boys in the class? Well, there's 3 boys out of a total of 8 students. So P is going to be 3 out of 8. The population in this case, the proportion in this case, is within the given class. If I then said a group of 4 students is randomly selected from that class, this is now a sample. So when it says proportion of boys in the sample, we're now going to use p hat to denote that it was from a sample of that, essentially a subset of the overarching overall global population. So in this case, yeah, the selection contained 1 boy and 3 girls, so your new denominator is 4 for a total of 4 students, and because there was 1 boy selected, p hat is going to be 1 over 4. That's pretty much it for the definitions difference. Are there any questions or clarifications regarding that? let's start looking at some of the typical questions you'll come across. A jar contains 4 white, 6 black. 3 balls are sampled at random, this time without replacement, so binomial is not going to be applicable here. Binomial would require with replacement. Find the probability that the proportion of white balls p hat is equal to a third. So fundamentally, p hat is just x on n, right? X is going to be the number of desired outcomes, and n is going to be the number of total possible outcomes. In this case, proportion of white balls means x is going to be the number of white balls that was selected, and n is going to be whatever the sample size was. In this case, it is 3. 3 balls have been sampled. So what you are solving is the probability of p hat being equal to a third, but it is equivalent to if you had just considered it like you would discrete and just say, cool, p hat equaling a third is effectively the same thing as just saying capital X equals 1, right? 1 white ball was selected. Because we've now converted it back to an equivalent discrete probability statement, we're just going to go ahead and use our discrete probability methods, of which there are 2 main ones you can go about for this because it was without replacement. One method of going about it would be using counting methods. You want to find your capital N, total number of possible combinations, and then figure out the number of desirable combinations. You can use your counting methods to achieve that. This is essentially just using the selections equation, NCR. So for that, if you're looking for your total number of combinations, there were 10 balls total, so your N is going to be 10, little n is going to be 10. And because you are selecting 3, your R is going to be 3. That's going to come out to have a total number of combinations of 120. From there, to get desirable outcomes, you're essentially going to do 2 NCRs back to back, which is one of them is going to be saying how many white balls you selected, and the other is going to be saying how many black balls were selected. So if we're looking for capital X equals 1, that means 1 white, and because we selected 3 total, that therefore means 2 black. So you're just going to do them each individually, and because this is a thing that is done in sequence, these are now multiplicative between them. So there were 4 white balls, you're selecting 1, that's why the N is 4 and the R is 1. And there were 6 black balls and 2 were selected. That's why you got N is 6 and R is 2 for the second fraction. Again, done in sequence, right? White, black, black, which is why we have a multiplication between the two, thus getting us our capital X of 60. That's 60 desirable outcomes divided by 120 total outcomes. Net probability is going to be equal to a half. All you would do then is, once you've calculate it in the PR X equals 1 statement, you'll just convert that back to the p hat statement, because it did ask you to solve for p hat equals a third. It's worth putting that in as your final answer there. If this stuff is fairly rusty, and it probably is for a lot of people given that it was Unit 1 and 2 that last discussed it, you can also just count the number of ways you could arrange those outcomes. Right, so for 1 white ball and 2 blacks, you could have white first, then 2 blacks. You could have black, white, black. You could have black, black, white. And then all you would do is just, figure out the probabilities of each of those individually. So for instance, getting a white, then a black, then a black, you are initially starting with 10 total balls, 4 of which were white. So 4 out of 10 for that first white. Then, when selecting the next black ball, because you've already selected a white at this point, the total number of balls has dropped down from 10 to 9. But the total number of black balls has not dropped because you selected a white ball specifically, which is why the numerator still remains as 6 from what it started. Then from there, selecting another black ball, again, the total number of balls is just consistently dropping every time you take one out. And because a single black ball has been taken, that 6 is now going to drop down to a 5. because these were all done in sequence. White was taken, then black was taken, then black was taken. All those probabilities are multiplicative. Exact same logic for the other two. They will all end up being the same thing, oddly enough. How rare is that? Probably not too rare, because you're always decrementing, the numerator's always decrementing in the same way, and because it's all multiplicative, the denominators, where they're located, isn't necessarily, because it's all multiplicative, where the numerators and denominators are doesn't really matter too much, because it's all just going to be multiplied up at the end of the day. And so yeah, not necessarily too rare to have them all be, or end up being the same fraction. Just don't necessarily count on that being the case always. I think I've definitely seen examples where they're not all the same thing, although that's just my memory, so it might be wrong. But yeah, those are the two main ways you could go about it. Manually figure out yourself how those combinations could be arranged, or literally use the dedicated counting methods for those things. Any questions? Okay, next up, how do we find a range of values? So what we just did there was calculating a specific p-hat value. P-hat is equal to a third. What if instead I wanted to calculate p-hat less than or equal to a third? How do I know how long that goes for? Again, we're just going to convert that to an equivalent discrete probability. We already said that a third was the same thing as x equals 1, so rather than saying p-hat less than or equal to a third, we now say x less than or equal to 1. From there, we would just set up our discrete probability table, and then, or at least visualize the discrete probability table, and then go from there. So for x less than or equal to 1, that would mean this outcome, and the x equals 0 outcome. Just for fun, here's the equivalent that you would write for the p-hat table. So rather than having all these x values, the p-hat values just end up being fractions of whatever your largest outcome is. So rather than 0, it's now 0 out of 3, which obviously goes down to 0. Rather than 1, it's 1 out of 3. Rather than 2, it's 2 out of 3, so on and so forth. This example is more or less the same as the previous example, so we're going to go ahead and borrow the answer that we had from last time. And all we're going to do from there is solve the missing thing, the probability of x being 0. Remember, with discrete, when it comes to finding the inequalities, you just find each individual probability in that interval and then add them together. So the missing one is probability p-hat being 0, or, probability of x being 0. So in that case, x equals 0 or p-hat equaling 0 just means no whites were selected, which means all blacks were selected, in which case, probably easiest just to multiply that up rather than going through a whole combinations, selections equation approach. That's going to get you 1 out of 6. Then just go ahead and slap that on to the half that you had from before, giving you a total answer of 2/3. Any questions? Cool. That's the fundamentals there. So basically just discrete. All you have to do is one stage at the very beginning, which is convert your p-hat statement into an equivalent probability of x statement, right? Converting your fraction into an integer. And then once you have that, you're now happy to go ahead and do exactly what you've done before with discrete or binomial, depending on what's relevant. Next up, some statistics. So the statistics are going to look similar to that of binomial. They're not going to be exactly the same, and they can look a little bit weird. Like for instance, when it comes to calculating the mean or the expected value for sampling and estimation, ends up just equaling p. Expected value of p hat is just p. The reason why is more or less because they're just talking about the same things. You know, expected value and p. If your expected value is in terms of a fraction, a proportion, then that's more or less what p is, the probability of a certain thing occurring. There's a bit of a math thing that they go through to show you like where the equation comes from that proves how this all works, and it pretty much just boils down to p hat being equal to x divided by n. It's trying to convert you back to binomial or back to discrete, and then because you are dividing by n, what you'll see is that rather than the mean being given by like np for binomial, because you've got that division of n through it, it just ends up being p. You'll find similar for the variance, and then therefore the standard deviation will have the same thing. You'll have this division of n in there where you otherwise wouldn't have. But you don't need to know where it came from. That's just more for a bit of trivia as to why they look similar but different. As a bit of a proof, you could do the mean or expected value the same way as you've been doing it for discrete before. It's obviously going to take a while, because if you recall, the way we do it is you take the x value and you multiply it by the equivalent probability, rinse, repeat, and then add all the results together. So how would that look for p hat stuff? Well, let's have a look at our example first. A coin is tossed 3 times, and here's our distribution for number of heads, right? So you can have 0 heads, 1 head, 2 head, 3 head, and all the probabilities are already given for you. If you wanted to do the mean of just this table, then yeah, you're doing x times the probability, so on and so forth. But we're not trying to do the mean of, we're not trying to do e of x, we're trying to do e of p hat. So we want to do it proportionally with fractions. So all that means is you're converting your x row into a p hat row. Once again, denominator will be 3 because 3 was the largest outcome. And then we do the exact same procedure for that. You know, 0 times 1 out of 8, a third times 3 out of 8, so on and so forth, adding them all up, and you'll get e of p hat is equal to a half. You can do that if you want. That's just to show you that that method still works. In reality, much easier to say a coin toss is 50-50 heads or tails, so my expected proportion is going to be a half. Much easier. Any questions there? So basically all that was happening at the end for the little cheat sheet, a little shortcut there, was to say that the expected value is just equivalent to the probability of that thing happening, whatever that thing ends up being. Here's the variance equation, so it's still just p's and n's, just like last time from binomial. It's just arranged in a different way. I copied down that proof here if you're interested in reading it from there instead, but not necessary. And then standard deviation is always the square root of variance. So if we're doing the standard deviation of a proportion, we're going to take the variance of the proportion and then square root that. So what's that going to look like for an example? Let's find out. A random sample of 4 items is selected from a box of 10 pens. There are 2 red, 8 blue. Calculate the standard deviation for the proportion of red pens. So one thing to reiterate there is that it really does matter which of the 2 outcomes or more outcomes you're wanting, because that'll determine what your, mainly what your p is going to be. The n is going to be based off of however big this sample is, but the p is going to be based on the probability of a success, which in this case is looking at red pens. So there are 2 reds out of a total of 10, so your p globally, remember p is not p hat in this case, you'll know the difference. When it has the hat, you're doing it through the sample. If it's just p, you're doing it globally. So yeah, box of 10 pens, and 2 of which were red, so 2 out of 10. Then for your N, you're looking at the sample size, not the global thing. So that's one thing to keep in mind that's different between binomial. Random sample of 4 items is selected from that box of 10. Since we're doing sampling and estimation, the N is referring to the sample size, not the global population size. We have our N, we have our P, chuck them in the spots, simplify what you get. If it was variance, you would just remove the square root. If it's standard deviation, which it is, you do have the square root. If you really wanted to, you could do variance the same way you've done discrete before. Don't. That's what it would look like. Just don't do that. You do get to the answer, yes, but that's more for fun, just to look at. Cool. So again, really not much has changed really. You're still just looking for P and N. It's just like where you source P and N when it comes to sampling and estimation. It's a bit different. Anything to clarify there? Okay. Last up, confidence intervals. Now what you might notice is that they have specifically called this an approximate confidence interval. And the reason why is because, well, I mean, the way I would think about it is that the way you interpret this confidence interval is a little bit different to how you interpret the other confidence intervals. When we're thinking about our other confidence intervals, it was always like, cool, you had some upper and lower bound, you had a 95% chance that your given result would be between some upper and some lower bound. That's how you would interpret those. How you interpret these is a little bit different. Firstly, let's have a discussion on the equation. So rather than having x in the middle, you have p hat in the middle of your interval. And you still have p hat plus minus some number of standard deviations. The only one they've ever asked for is a 95% confidence interval for approximate, for standard deviation, for sampling and estimation specifically. And for whatever reason, they care about a number of decimal places now. They're saying to refer to rather than say 2 standard deviations, which as you can think of as Z standing for, it's now 1.96. Again, this will be a calculator thing, so this will just be on your formula. Sorry, not your formula sheet, it'll be in your bound reference. So you just put this somewhere in your sampling and estimation section, and you'll be fine. Alternatively, you could even, if you wanted to, calculate those Z values based off of the inverse normal for your standard normal distribution, but better off not needing to do such things. Actually, the other thing that you can do is with the CAS as well. The CAS can actually calculate these values for you. Let me just figure out where it was. I think it's in the statistics menu. Yeah, it is. Menu 6.6, confidence intervals, 1 prop Z interval. If you pop that up, the only thing that's a bit weird about it is you've got to split your p hat into the x and n. So like if your p hat was a third, for instance, that might mean you've got x equals 1, n equals 3, or it could mean that you had like x equals 10, n equals 30. The difference does actually matter. So make sure you use the actual numbers, not necessarily just looking at the simplified p hat and then splitting them up. And then all you do is you put your confidence level, which is pretty much always going to be 95%. So actually, just to explore that real quick, let's have a look. So let's say we're splitting up our p hat into x equals 1, n equals 3. You're going to get a relatively nasty looking table, though it's not too bad. The thing you're going to care about is the C lower and the C upper, and maybe the p hat value itself. You should already know the p hat value by the time you're plugging this stuff in, but it's nice to have a look at it and say, yep, that's definitely a third. That's what I was expecting. C lower is the lower bound of your interval, C upper is the upper bound of your interval. If we then do that again for, using a larger n, what you'll find, I'm just control entering to knock off the fractions. What you'll find is that your lower and upper bound shrink significantly. If we look at the previous one, it was from a negative number to 0.8. This is now from 0.16 to 0.5. Exact same p hat value, having a larger n shrinks your interval. We'll do it one more time, another factor of 10. Instead of saying 10, we'll say 100, and we'll have n as 300. And you can see that as n increases, the gap between your lower bound and upper bound is shrinking quite significantly. We're now all the way down to 0.28, 0.38. That's a gap of 0.1 versus a gap of 0.34-ish. So it has a pretty drastic effect on the lower and upper bound, which isn't really present in any of the other confidence intervals that you do. The reason why is because it's proportional, and the other reason why is because when you're doing approximate confidence intervals, what you're actually doing is trying to estimate p hat based on your sample. So n is always the sample size. In this last example, you have a sample size of 300, and x is going to be the number of things in the sample that met your outcome, whatever you wanted. P hat for that given sample. Sorry, I'll say it again. Your lower and upper bound are essentially setting boundaries on where the true population proportion is likely to be. Because, let's say you are investigating, likelihood of students passing a class. Sure. You could look at a single cohort and get a sample there. You could look at a single school and sample across all cohorts. You could look globally across the entire world, probability of someone passing a particular class. Now I know the metaphor is breaking down there, but the idea is to say that whenever you're doing these statistics, whenever you're collecting your data, you're not ever looking at the total population that could be relevant to what you're doing. You're always doing surveys, and there's only a certain number of people that will ever respond to that survey. You're not going to get the entire population ever. And so what you need is a method by which to estimate what the true population proportion is. That's what this is. You're setting some lower bound and some upper bound on what the you're setting some lower bound and upper bound to constrain where that true population proportion is likely to fall within. And as you increase your sample size, that's why the lower and upper bound shrink ever so slightly closer and closer to the center. Because as you increase the number of samples, the likelihood, increase the sample size itself, the likelihood that your p hat value, your estimate, is close to the actual population proportion rises significantly. I spent a lot of time talking about that specifically because there are questions in the SAC, or more specifically the exam, that say, interpret the interval. What did you just find? And these are the sorts of things you would need to briefly discuss. Maybe to give a visual on what this might look like, if you have a look back at the screen share, what I've got here is basically each of these dots are different samples of different p hat values for groups of 100 people. So, the example here I'm giving is sampling group of 100 people and find the proportion of people with blue eyes. If I do that once, I might get 30 out of 100. If I do that again with another 100 people, I might get 27 out of 100 that time. If I do this over and over and over again and dot all those out, what I'll find is I'll basically get a normal distribution with a center. Whatever that center is my most likely or best estimate for the true population proportion of people with blue eyes. And the confidence interval, depending on how big your n is just constraining where your upper and lower bound is. You know, if you have a low n, you might be looking quite wide. If you have a very, very tall n, or large n, you might be looking, you know, just within plus or minus here, a much smaller boundary. So this will get you maybe 1 or 2 marks on the exam to be able to explain what you found should it come up. It has come up before. Worst case scenario, you just give this a read in your bound reference and you're like, cool, okay, I'm just going to copy down the bold and then put the words in that matter for that particular question. That's your worst case scenario. If you need to do this tech-free, you can. You just use the equation. It's fairly rare to need to do these tech-free, but they have shown up before. You'll often be given a Z value to work with. You're not going to be forced to use 1.96 in a tech-free. That'd be quite cruel. They'll often just say, hey, use Z equals 2 for your interval. And so if you're doing this tech-free, all you need is p hat, Z, and n. Z is a given already as 2. P hat you'll calculate maybe, or just read it off the question, and n is always going to be the sample size. So in this case, n is 1,000 because the survey was 1,000 people. 55% of those exercise on a regular basis, so your p hat is 0.55. It's always proportional, not an x value specifically. Because, you know, if you wanted to convert this to an x value, you just say, okay, 1,000 times 0.55, whatever that is the actual number of people who consider themselves to exercise on a regular basis. But we're doing sampling and estimation, so just use the proportion rather than the physical number. And then, yeah, whatever comes out of that calculation is your interval. You can see n being 1,000, the interval's fairly tight. That's about calculating the intervals. The other reason you might care about that equation in a tech active scenario would be because you can use it to calculate p hat or n, so long as you already know what the interval is. And this is a very common question actually for like a multi-choice, and a surprisingly low percentage to solve. I don't really know why. It's fairly trivial to solve, especially the p hat. So basically what's going on here is it's saying, hey, we got a 95% confidence interval. Here it is. Just by looking at the interval and knowing it's a 95% confidence interval, you can actually figure out what sample proportion and sample size was used by the interval, which is kind of strange to think about, but you can. So what do we do from here? Well, the easiest of those to calculate is p hat. Why? If we look at our equation, actually we'll go back here. P hat is just the center of that interval. You got p hat plus and minus either side of a center. So whatever the center of that interval is p hat. I have an interval, just do the midpoint. Whatever the midpoint is our p hat. Nice and easy. How we get n is a bit trickier. You now have to actually make a choice here. You have a bit of freedom. What you are now using is the equation for the confidence interval. So you're using this equation. You have z, whether you're using 1.96 or 2 will be based off of... Yeah, will you get this question in a tech-free? You could get this in a tech-free. So yeah, whether you use z equals 2 or z equals 1.96 will be based on whether or not it's tech-free or tech-active. You already have the p hat, we just calculated it. Z is a given based on tech-free or tech-active, and n is the only unknown left. Each of those sides of the equation, of the interval, are two separate equations. So it doesn't actually matter which one of these you use, because both of them contain the exact same variables, and all that's going to matter is if you use the upper bound, just make sure when you use the upper bound with the plus, you put the upper bound to equal it. Because remember, we already have the interval in this case. We know what the interval actually equals for the upper, and we know what it equals for the lower. So, whoops. So whatever side of the equation you use, whether it's the plus or the minus, just remember that the minus always goes with the lower bound one, and the plus always goes with the upper bound one. Doesn't matter which one you use, both of them will get you the n equals 168 that you're required to have. Any questions there? The other question that shows up in a short answer part of the extended response, of the tech active, is to determine the effect of increasing n. So we already actually explored this already when I was increasing n by a factor of 10 a bunch of times. The width of the upper and lower bound was shrinking. So again, if I pull up the calculator, if we look at the C lower, C upper, it started out quite drastic. In fact, this is almost a gap of 1. The sample size was so low, n equals 3, that the gap is practically just 1, which is quite awful. Bringing that up to 30, we now have a gap of 0.34-ish. Bringing it up to n equals 300, the gap is now 0.1-ish.
Sorry.
Yeah, question?
Visually represent this when you're doing CAS somehow?
Could you repeat that? It kind of cut out a little bit.
Oh, sorry. Could you visually like show how this would work on a CAD? Like not on a CAD, but on a graph or on a normal distribution?
Could you visually show how, like, how the gaps are shrinking?
Just yeah.
Yeah, you could. It would basically be, if we go back, where did I do the drawing? It would basically be you drawing a sequence of these distributions with different. I'll just draw it. So if I were to try and sort of represent how things were changing, I might do something as follows. So for like n equals 3, you'd have your distribution, some lower, some upper. In this case we had like negative 0.2 and like 0.8, I think, and that was your 95% confidence interval. Then to show the shrink, you'd have n equals 30, have another distribution, the exact same spacing but with the updated numbers, which if I use the actual ones, we had 0.16 and 0.5. 95%, and the p hat in each of these cases, if you wanted to put it there as well, was always a third. A third is always the center of it.
Okay.
That's all fair enough?
Yep.
Cool. Okay, so yeah, that was just a refresher on, as we increase n, the gap between our upper and lower bounds shrink. Now, that's not quite good enough to say for a final answer. If we look at the actual specifics of the question here, we're given the confidence interval itself. We're then told a larger sample of households are selected, with a sample that is 4 times larger than the original sample. P hat is going to be the same in both cases, or it's just assumed that P hat is going to be the same to make sure they're actually comparable to each other. The question is now, by what factor will the width of the confidence interval be decreased? So it's not just good enough to say, yep, we're using 4 times n, that means my sample, that means the width should decrease. You want to give the specific factor by which it is. decreased. There's a bunch of ways you could do this. I've seen a couple of ways. I think the most understandable way to go about it would be to write it purely algebraically with whatever information you have, and try to keep it as high level as possible. Putting more numbers in there kind of just complicates things. So the thing to understand here is that the width of your confidence interval is always just 2 times the standard deviation term. Alright, if we look like way back to the equation, it was p hat plus this value and p hat minus this value. So if you go, you know, right by this and left by this, the same number, it's essentially the width is now just double whatever that was. Which is why I'm saying that the width is given by 2 times that standard deviation term that we have. I've called it width 1 specifically because I'm referring to the initial sample that we have. With 2, I am now doing the exact same thing, but introducing the new information. It's that I now have a 4 times n, 4 times bigger sample size than I did before. So the equation's basically the same, except n is now being replaced with 4 times n. From here, the easiest way to then compare the two is to make sure the coefficients are located in the same sort of area. So all I'm going to do is distribute the 4 outside of the root, or I guess more specifically factorizing the 4 outside of the root. By doing so, that will become a factor of a half, and the 2 and the half will now cancel. You now have something that is much easier to compare because the factor is now a bit more obvious, right? So initially we started at 2z times the root. We now have 1z times the root. This is 2 times smaller. So by increasing your n, your sample size, 4 times, you shrink your interval in half from what it was initially. Because it asks for a specific factor, you say decreased by a factor of 2. So this is how you would more or less do that. You do have enough information to figure out what your p hat value is. It just doesn't really help because all you really care about is making these equations look as similar to each other as possible, and then that way it's easier to compare. You can imagine if you calculate your p hat, put it in there, and then do all the arithmetic to simplify things, it just doesn't really help that much because all you're trying to do at the end of the day is compare the factors. This is a pretty low percentage question as far as like how well people do at answering it, so this will be a really, really good one to have on your bound reference. You don't need to necessarily have it memorized, you just need to understand the rough approach and then be like, okay, cool, I'm just gonna either bring things outside of the root or bring them into the root. Another way of doing it, should you wish, could be to bring this factor of 2 inside of the root, although things get a bit weird when you do that, or at least it looks weirder, in my opinion. Okay, that's it. That's all the content. We have now officially completed Unit 3.4. All you gotta do now is practice it. Anything that I should clarify before we get into some of the practice?
So that's it for prob.
Yeah, that's it. We've looked at...
It's pretty short.
Yeah. Yeah, and a lot of it is just you doing discrete. Like, if you remember, like the first little half that I was talking about was just, okay, you have your p-hat equation, just flip that right back to discrete, and then just do what you do in discrete. For statistics, it's still just n's and p's, just like binomial, just putting them in slightly different spots. Only thing that had a bit of weirdness to it was the approximate confidence interval. Yeah. I think 17b, does that talk about it? Yeah, you get a whole... you can read like this explanation of what you're doing with the confidence interval, but they really seem to love making it look more complicated than it is. So maybe don't worry too much. Oh, actually the other thing, in the book, they care about margin of error as a particular thing. It's not it's not a thing that's shown up on the exams, but because it's in the book, it might show up in your SAC. So I'll briefly touch on it. It's nothing hard. The margin of error is essentially just one side of your confidence interval from the center. That's it. Like if you recognize this one, 95% confidence interval, 1.96 is your Z, and then, well, there's your P hat and all that sort of shit. That's just literally one side of your confidence interval. So if they're saying calculate a margin of error, they just mean from center to right or from center to left. It's the same number either way. What is that term? That's all I mean by that. It's a very simple thing, but nothing to worry about for the exam. Cool.
What are the most like common things that show up on the exam?
Yeah, so most common by far is going to be like these fundamentals here of just saying, hey, p hat is a third, or p hat greater than or equal to a third. Calculate that. So the skill of being able to flip your fractions into integers equivalents and then going through and doing either binomial or discrete, that matters quite a bit. Statistics are relatively frequent to show up. And then how likely are these? I mean, most of the questions that come up with this are either going to be calculating the interval, which is just a freebie in basically every case, because you've just got a CAS thing that you can press and then it just gives it to you. Or it might be something like this, which is a bit less likely. This is least likely, although it has happened before. So worth having it there. I mean, how we could even... Yeah, question?
Oh, so I was gonna ask like you know, kind of like for take active, like sometimes for SACs you get like this. It's like question one has like A, B, C, D, E, F, G. Like,
Yeah.
is it sometimes in the exam where it's like, say, like part A or B is like on prob, and then C or D is on like other topics?
Oh, not like that. No. So probability is sort of self-contained in its own little thing. Like if we find the probability section on this one, question 3, it starts out as continuous, still continuous, definite integral. Pretty sure this one goes to binomial because you're now starting to talk about multiple days in the week rather than just a single day. So it flips to binomial. P hat, you now know what this is. So, you know, finding probability of between 0.4 and 0.6, what you now need to do is, well, read the question properly. What's actually happening here? Okay. I think I would need to read into this a bit more to figure that one out. But basically you're going to have some n, some sample size, which will be your 5-day working week. Yeah, actually that's exactly what it is. So n is your 5-day working week now. And then, you know, 0.4 equals x over n. What's that? Actually, what's that going to be? 40% of 5. Let's calculate that. 0.4 of 5. Yeah, that gives you 2. And then 0.6 of 5 is probably going to be 3. So it's now, instead of doing from 0.4 to 0.6 of p hat, you're now doing from 2 to 3 of x. It's now binomial. You've got n equals 5. You've got your lower bound of 2. You've got your upper bound of 3. And your p value came probably from here, or something equivalent to a previous question. But as you can see, as we keep going, you know, normal distribution now, probability, it's all probability, it's all self-contained in its own question. Yeah, and usually for Tech Active it's only like, you know, because there's so few questions, it just takes up like one of the 4 or one of the 5 that you get. Make sense?
Yep, that's all good.
Yeah, and so I've said this a couple of times, but the main skill isn't necessarily being good at any individual probability type. It's trying to identify when does it change. And actually, maybe that's a good thing we can because we don't really have too much time to practice too many of the questions. Maybe we'll save that for the review class. Maybe it's a good idea for me to start exploring, okay, cool, we've learnt all these concepts now, how do we figure out when things are changing? Yeah, question?
Yeah, I was just wondering like what the rest of the year is going to look like, I guess, up to the exam in early November.
Yep, so up until now, because we've covered all the content, we are going to grind out exclusively probability until everyone's done their probability sack, and then we will grind out exclusively past exams. So we can all practice that. Unless, of course, like, we find that for whatever reason someone's having trouble with a particular topic, you guys can submit questions just like normal, or topic recommendations, and we'll do little focuses on that for at least for the Class 2 stuff. Class 1 has still got a bit of content to cover. But yeah, this is what Class 2 is going to look like.
Yeah. Okay. Yeah, because I've got my method sack on the 3rd of September, so a bit early.
3rd of September. Yeah.
As in my prob sack.
Yeah. That'll be that's the last one for everyone. Unit 3-4.
Yeah.
Yeah. I think for most calendars, for most timetables that I've seen, we are about a week ahead on content. I think most people are looking at normal distribution this week, and we have finished sampling and estimation this week. So it's good having, what's that? How many weeks have we got? 1, 2, 3. It's about 3 or so weeks to, continue grinding out those kinds of, or figuring out basically when to use what, which I think we'll spend the rest of this lesson discussing. So, okay, with that in mind, how do we master this kind of flow? Like, how do we understand? How was I able to quickly say, that's just continuous, this is still continuous, this is probably binomial, p hat is sampling and estimation, how do I know, like, this is discrete? What am I looking at there? So, let's have a look. As far as the question structure goes, you'll often have 2 parts to it. You've got some background information, and you've got the actual problem statement. This is true across literally all of methods. You'll have you might have your f of x or your whatever, and it says calculate derivative or whatever. That's what I mean by the problem statement. It's what it's telling you to actually do, and the background information just gives you all of the stuff that you need to actually solve that thing. Is this our bound reference? Yes, this is the probability bound reference. This is located in the probability section in our modules. I think it has its own dedicated folder called bound reference. And this is the very top of it. You can see it's quite an extensive document. You might not want to print the whole thing off because it's basically got every goddamn example I could find. And I tried to give them reasonable titles, but there's really only so much you can do to label these things. So the first half of it, well, I guess the first third of it, talks about the key concepts and things you need to understand about how you break down these questions. And next bit after that are the individual functions themselves, like that you use for the CAS or the actual equations. And then everything else from there is examples after examples. Safe to assume probability sack will be tech active. Yeah, I mean, unless there's like 2 parts to it, maybe you might have a part 1 tech free, a part 1 tech active, a part 2 tech active. But yes, you will definitely need a tech active part because of the normal. I mean, I guess you don't technically need it tech active, but there's so many things built into the CAS that you need to be able to be good at that it would be a really bad idea for your teacher to give you a tech free only probability sack, because that's just, not preparing you for anything. Or at least not preparing you nearly as much as it should. So yeah, very likely to have tech active parts, almost certainly. But okay, so identifying the type of probability. How do you know at a glance what type of probability that you are working with? So it's often the case in those extended response sections you're going to need to consistently reevaluate, has my probability type changed? What is it about this new background information that may or may not change if I'm now working from binomial to continuous or whatever? So, to identify if you have binomial, you're looking for a number of outcomes and whether there are repeated trials, whether it's independent, whether those repeated trials are independent. So binomial has to have two outcomes. So when I was looking at this and I said binomial, it's because I saw late, find the probability of being late on at least one day in a 5-day working week. Right, so you're either late or you're not. That's binomial. You have a number of trials, and I didn't really look too hard, but the probability that was mentioned earlier was probability of being late on any given day, and it says, actually, there it is, keyword independent. So those three things together, independent, maybe there was only two things, independent, two outcomes, and a clear n, is why I was able to say binomial for that. Here's some other keywords to look for, but yeah. Next up, discrete. How do you identify discrete? Well, there's going to be a big table. Like, when I had to scroll through here, I saw this thing, that's discrete. Like, you got outcomes A, B, C, the relative probabilities of each of those, and here's another table for you to complete probability distribution. Now, binomial is a subset of discrete, so it might very well be the case that you still can calculate this stuff binomially, especially since I'm now looking at it a bit harder and I'm looking and seeing independent. So yeah, might be the case that binomial, although the fact that it's A, B, C, three outcomes, without reading any deeper, still probably reads as discrete probability rather than binomial probability, simply because binomial needs two outcomes. But yeah, as I said, there tends to be a lot of crossover with binomial here. Next up, how you know whether you have normal distribution? It will always tell you. Modeled by a normal distribution with mean of whatever, standard deviation of whatever. So the question will always tell you whether you now have a normal distribution. Nice and easy. Continuous probability, or probability density functions. How do you know that? There is an f of x in a probability section. If it says find the mean, find the standard deviation, find the probability, continuous random variable, all of these are indicators that what you have is continuous probability. You've just got this big f of x piecewise, it's a dead giveaway. Sampling and estimation, you're going to see a p hat in there somewhere, or you're going to see the keyword sample. In this case, you see the capital P hat, nice and easy. You see the word proportion, you see your P hat again. That's your indicator that, once again, probability type has changed. You now need to recontextualize what you're looking for. Lastly, there are some just general probability questions that will show up. I might be able to spot one in a multi-choice. Let's see if we can find it. No, not really. Random sample, you can already see is a sampling and estimation thing. Keyword approximate 95% confidence interval, we just talked about that. You can see the interval. And here's that question, right? Calculate n. So there's one that you could practice on from the 2025 exam too. But not quite what we're looking for. Yeah, we're looking for this thing here. This is just your general probability stuff. These are usually stuff you solve with like tree diagrams. It's where you've got walk or different form of transport, and then from there time it took. Right, so you've got these two things that you're looking at back to back. What transport they used, how long it took. This is where you branch it out into two separate, into your tree diagrams. This is just general probability stuff. It doesn't really fall into a particular category. You could definitely rationalize a particular category for it, but it's just not helpful to think about it that way. As far as like probably the sneakier crossovers, binomial, discrete, sample proportions, those are all in the discrete category, and so it can be a bit, yeah. These are very likely to be, done back to back on each other. Transferring to continuous stuff with the normal distribution, what you'll find is that you'll often use normal distribution stuff to calculate p-values for your binomial, which we had a similar example of here where we use continuous to calculate p-values. Because, it said, well, we didn't necessarily need to calculate it, it was given to us. It said, write a definite integral, prove probability of late is this. Then, when you're doing the binomial version of that, when you need your p, there's your probability of late. You may need to either calculate it, or it might just give it to you from the continuous or normal distribution, depending on depending on where it came from. I know we're hitting time here. I'll just, continue on with a bit of this, should anyone be interested. But if you guys got to go somewhere, feel free. Happy that you came. So, once you've identified what type of probability you have, you want to care about the key parameters. So, for binomial, it's always just NP. Maybe you're given the mean or standard deviation. And then just here's some other stuff that may or may not show up. It's pretty much just a broad statement of, all the things that you can be asked about. Discrete's very similar. Again, you might be asked about the mean or given the mean, standard deviation, variance. Usually you're calculating statistics with discrete, but the other alternative is calculating the probabilities with discrete as well. For normal distribution, you care about the mean, standard deviation, any z stuff that's related, and maybe some upper or lower bounds if you're given them, like the actual x values themselves, because you're often using that z equation to do sorts of questions. For your continuous probability, the key things that could come up would be your mean, standard deviation, median. Average value of the function may be given. I don't really know what I meant by that, to be perfectly honest. Yeah, not too sure what I meant by that, to be honest. Anyway, those are going to be the main things that'll come up, and then it might ask you about, solving probabilities using integrals. Lastly, for sample proportions, the things that matter are going to be p hat, n, and your standard deviation. Those are the only terms that show up, and then you might use those to calculate your confidence intervals. Otherwise, it'll just be a matter of calculating probabilities, which is just a matter of flipping your p hat to an equivalent x statement. And then from here, I've just got some general probability stuff that might come up. And then it just goes into more detail as to exactly, what equations, what tools you have available to you in each of those sections, and the CAS functions. So it's a big old document that you can, if you find it useful to have, feel free. It's a nice bound reference. I got a fair few compliments for it, which is probably the first time I made a document and they're like, yeah, shit, this is good. And then from there, it's just, the specifics of the question, and from here onwards, it's just example after example after example after example. That's about it. Oh, actually, there was a... Is this what I meant? Holy shit, I can't believe I actually found that. I was talking earlier about not really knowing what I meant by the average value, but yeah, okay, so that has background in continuous probability, because area under a curve is what continuous probability is all about. So if you know the average value of the function, just remember your average value formula, and then yeah, because you now are introducing integrals into that, you can now sort of retrofit it back via a sequence of whatever to eventually get your answer that you're looking for. One question, and I put it in as a bullet point. That's kind of funny. Anyway, there's like a billion things in here that you can have a look at for examples on how to do things. It's, as a reminder, located in the probability section bound reference. Cool. That's about it. I'll leave you guys to enjoy the rest of your day, unless you'd like me to quickly clarify anything.
Thank you.
No worries.
Thank you.
All good.
Have a good day.
You too.